So a unit ramp input is applied to the system shown in the adjoining figure. The steady state error in its output is, open loop transfer function is 2 by s into s plus 1, right? This is g of s, right? So you have to calculate kV for calculating error for unit ramp input. kV is limit s approaching 0, s into g of s, that is equal to 2 by 0 plus 1, that is equal to 2. Therefore unit ramp input, which means A is 1, A is also 1, therefore ESS is equal to A by kV, that is A by 2, that is 1 by 2, that is equal to 0. So let us solve the next question now. The unit step response of a unity feedback system with open loop transfer function g of s is equal to so and so is shown in the figure. The value of k is. In majority of the questions you will see unity feedback only, you won't see other than unity feedback. Generally GATE board gives unity feedback systems only. Unit step input is provided. See, the magnitude of input is 1, whereas the output is something like this. Steady state value of output is how much? It is 0.75, right? So this is output, whereas this is input, right? So it is given to be a unity feedback system. The difference between output and input, how much is that? Difference between output and input is 0.25. Yes or no? Between 1 and 0.75, the difference is 0.25. Therefore, ESS is equal to A by 1 plus Kp, that is 1 by 1 plus KDC. KDC is K by 2. If you put S is equal to 0 in that, KDC will be K by 2, right? So this is equal to how much? 1 divided by 4, which means 1 plus K by 2 is equal to 4. 1 plus K by 2 is equal to 4. That means K is equal to 6. So this is one approach. You can use this approach, right? One more approach which we can use is the DC gain approach. So what is the closed loop transfer function? Closed loop transfer function is equal to G by 1 plus G. You can write it, right? So it will be K by S plus 1 into S plus 2 into S plus 2 plus K. This is the closed loop transfer function, right? So to this system, to this particular system, this is the entire system, right? So to this particular system, we are giving a unit step input of magnitude 1, and we are getting a steady state value of 0.75, which means after feeding a DC input of magnitude 1, we are getting a DC output of magnitude 0.75, which means the DC gain is how much? 0.75 divided by 1, that is DC gain is 0.75. You can write it as 3 by 4, right? DC gain is 0.75, that is 3 by 4, right? So DC gain is nothing but S tends to 0 overall transfer function, limit S tends to 0 overall transfer function. This is DC gain, right? Put S is equal to 0 in this. K by 2 plus K is equal to 3 by 4, which means 4K is equal to 3K plus 6. K is equal to 6. You can calculate using this approach also, right? So if at all these did not strike, just blindly go by the mathematical method. What is C of S? C of S is overall transfer function M of S multiplied by R of S. What is R of S in this? R of S is equal to 1 by S. Therefore, overall transfer function is K by S plus 1 into S plus 2 into, S plus 2 plus K. This multiplied by 1 by S. This is C of S. The steady state value of C of S is given to be 0.75, which means limit S approaching 0, S into C of S is equal to S into this. SS gets cancelled. You will be left with limit S approaches 0, K by S plus 1 into S plus 2 plus k, that is equal to 3 divided by 4. From this you will get the value of k is equal to 6. So one is the steady state error approach, the other is DC gain approach, and the other is final value of C of S approach. All are same. All are same. DC gain, I'm just finding out the DC gain. See, this is the system given. G of S is the open loop transfer function, and it is a unity feed, and it is connected in a unity feedback configuration like this. To this system, I'm feeding R of S is equal to 1 by S. I'm feeding a unit step input. I'm getting a steady constant value of DC, right? See, any DC may have some transients also, right? What is the steady state value? That is nothing but the output DC value, right? So I'm calculating the ratio of output to input. Ratio of output to input is nothing but gain. So how much did I get it? That is 0.75. The DC gain of this system is 0.75. I've equated the DC gain to 0.75 and I got the answer, K value, right? So all these are approaches for this particular problem, right? You can use any approach. A system with transfer function G of S is equal to 1 by S square plus 1 has 0 initial conditions. The percentage overshoot in its step response is. So you have to find out the percentage overshoot in its step response. Steady state maximum peak overshoot in percentage is equal to e power minus pi zeta divided by under root 1 minus zeta square into 100. That is equal to e power minus pi into 0. 0 divided by under root 1 minus 0. Right? E power 0 is how much? E power 0 is 1. 1 multiplied by 100 is 100%. That's it. When zeta is 0, the steady state, the maximum peak overshoot is 100%. Dominant pole concept. See here, let us assume we have a transfer function something like this. The transfer function is some T of S is equal to 6 divided by S plus 1 into, this is our transfer function, let us say, right? So obtain the impulse response for this transfer function. Impulse response, that is h of t. Obtain h of t for this. So impulse response h of t is nothing but, h of t is the Laplace inverse of the transfer function. Laplace inverse of your transfer function is nothing but impulse response, right? So therefore impulse response, in order to find out impulse response, you have to partially obtain the partial fractions of t of s. T of s is equal to a by s plus 1, b by s plus. So tell me the values of a and b, right? So now h of t, what about h of t? H of t is equal to Laplace inverse of t of s. So I have already written it here. Laplace inverse of t of s, that is equal to 6 by 5 e power minus t minus 6 by 5 e power minus 60, right? This is the impulse response. So if at all you want to obtain the impulse response, how can you obtain? Just obtain the graph of this, the impulse response of this with respect to time. I'm going to obtain h of t, the impulse response, right? So you have to obtain the graph of, in order to find out this, put s is equal to minus 1 in this. If s is equal to minus 1, this is 6 by 5. This is correct, right? So h of t, in order to obtain the impulse response, 6 by 5 into e power minus t and minus 6 by 5 e power minus 60. Both of these has to be obtained. Yes, right? So 6 by 5 into e power minus 60. So what is its starting value? It starts at 6 by 5. It starts at 6 by 5, right? 6 by 5 e power minus t, let us say. So it starts at 6 by 5 and it will decay like this, right? Whereas 6 by 5 e power minus t, this is 6 by 5 e power minus 60. I'm mentioning it here. This blue one is 6 by 5 e power minus 60. Whereas this red one is 6 by 5 e power minus t, right? So this is the response, right? 6 by 5 e power minus t separately. Right? I'll plot this, I'll subtract this from this. I'll plot this and this separately and I'll subtract this from this. Right? That is what I'm doing. Is it clear? Right? Out of 6 by 5 e power minus 60 and 6 by 5 e power 60, among these two, which one decreases faster? Which one decays faster? Minus 60 or 60? Sorry, minus 60 or plus t? Sorry, minus t. Out of 6 by 5 e power minus 60 and out of 6 by 5 e power minus t, which one decays faster? Minus 60 will decay faster, right? So the response because of this minus 60 is decaying faster, right? If I look at the overall response, if I just want to plot the overall response, see here, the overall response will start at 0 and it will follow this for the remaining time like this, right? So this is the overall impulse response. This black one is complete response, that is h of t. So only for a short time it is not along with this, right? For the remaining time, this is along with this particular factor only, right? So you can say the response, overall response is completely similar to this, right? Yes or no? The overall response is coinciding with this. That is the reason why you call this as dominant response, dominant contribuent in the response. Is it clear? Whereas this blue one, you can call this as insignificant. This is insignificant. This is dominant, whereas this is insignificant. Is it clear? Yes. So from the transfer function itself, you can say that, see, the response because of this factor is dominant, whereas response because of this factor is insignificant, right? So you can call this as insignificant factor, whereas you can call this particular factor as dominant factor, right? So what I want to do is, this dominant factor is contributing more in the response, which means I just want to approximate. See, because of two poles, complexity increases. As the number of poles increases, complexity in analysis increases. I just want to reduce the analysis complexity. So I just want to reduce the system. I just want to reduce a higher order system into a lower order system, right? I'm just going to approximate this higher order system, this second order system, into a first order system. That is what I'm going to do now, right? So using dominant pole concept, what I'm going to do is, I'll just reduce a second order system into a first order system. Before reducing, what you must check is there are two conditions, right? So there are two conditions should be that there are two conditions that should be satisfied, which in order to approximate a second order system into a first order system, there must be two conditions satisfied, and the conditions are like this. First condition is, see here. So note down, before eliminating the insignificant factor, first one, make sure it is at least 5 times far away from the j omega axis. Sorry, this is not insignificant factor, insignificant pole. Make sure it is at least 5 times far away from the j omega axis than the dominant pole. So we have two poles in our system, right? So this is our S plane, let us say, and within the S plane, our system has two poles. One pole is at -1, the dominant pole, and another pole is at -6, right? So this pole can be called as insignificant pole, whereas this pole is dominant pole. So response because of the dominant pole is dominating, right? See, whichever pole that is nearer to the j omega axis, nearer to the origin and nearer to the j omega axis, is called as a dominant pole, right? So if the distance from the dominant pole to the j omega axis, how much is it? It is 1 unit. The insignificant pole must be at least 5 times more farther as compared to this. See that what is its distance from the j omega axis? It is 5. It is 1, right? 5 times of 1. How much is it? 5 times of 1. It is 5, right? So it must be at least 5 times far away from the origin, which means its real part should be less than -5. Its real part should be less than -5. So poles which are lying in this region, to the left of this, poles which are lying in this region are insignificant poles, right? So poles which are lying to the right of this, you cannot eliminate them, right? So see here, so this is, we have two poles in the system, one pole nearer to the origin and another pole away from the origin, right? So the pole which is nearer to the origin, is termed as dominant pole, and the pole which is far away from the origin is termed as insignificant pole, because majority of the response is because of this only. You have seen the response curve, right? Majority of the response is because of this dominant pole only, right? And the response because of this insignificant pole is completely insignificant, right? If we have a pole at 0.5, let us say we have one more pole here at 0.5, minus 0.5, like this. So -1 is not 5 times greater than -0.5. So you cannot eliminate -1, right? So this -5 is more than 5 times far away from the 0.5, as well as, -6 is more than 5 times far away from the 0.5, as well as this -1. So you can eliminate this pole, but you cannot eliminate these two. But that would not be insignificant for -1, right? So only those poles are considered to be insignificant, right, which are at least 5 times far away from the j omega axis than the dominant pole. They are at least 5 times far away. Is it clear? So just we'll solve one or two problems, you'll automatically come to understand. Is it clear? So just solve one or two problems, you'll come to understand it automatically. Right, the first condition is make sure it is at least 5 times far away from the j omega axis than the dominant pole, right? So whatever the dominant pole you have, the distance of the insignificant pole must be at least 5 times the distance of this. At least 5 times the distance of this, right? So just solve one or two problems, you'll automatically understand. And the second condition is, see, how are you approximating a second order system to be a first order system? By removing one pole. Which pole are you removing? Insignificant pole, right? So insignificant pole, you are doing what? You are removing insignificant pole. Before removing that pole, see, if you remove this pole, before removing that pole, what is the DC gain of this? Right. So the DC gain of this before removing the pole is 1. So if I remove this pole directly, what is the DC gain of this? If I remove this insignificant factor directly, what is the DC gain? 6, right? So what is happening is, if I remove the pole directly, the DC gain is getting affected. Right? So in order to avoid that, what I should do is, see, I should have to convert this into time constant form, right? So the second condition is convert the insignificant factor into time constant form before removing it, right? So if at all I want to remove this insignificant factor, what I have to do, I just have to convert this into time constant form, right? So the thing I should do here is, I just have to convert this factor into time constant form. Just you have to convert this into time constant form, right? So now this is going to be equivalent to what? It is 6 divided by s plus 1, and this is converted into time constant form. How can you convert this into time constant form? By taking 6 to be out of this factor, right? 6 into s by 6 plus 1. 1 plus st, right? This is converted into time constant form or not? Now this is converted into time constant form, right? So this 6 and 6 gets cancelled. What is left? It is 1 by s plus 1 into s by 6 plus 1. Now you can remove this particular factor. You can easily remove this factor, right? If you remove this factor, the thing which is left is 1 by s plus 1, right? Therefore the approximation of 6 by s plus 1 into s plus 6, this is a second order system. The first order approximation of 6 by s plus 1 into s plus 6 is 1 by s plus 1, right? 1 by s plus 1 is the first order approximation of 6 by s plus 1 into s plus 6. Is it clear, everyone? Is this clear? Yes, Hubli Electronics batch, DC gain should be same. See, the thing is, the response of the approximated system as well as the response of the given system, both should be same, right? At least if they are not completely same, they should be approximately same. That is what we are doing it, right? So we are making sure the response is not changed if we are approximating this. That is what we are doing here. That is what we are doing here. Is it clear? So even if the DC gain is changed, the response is changed. Yes or no? Right? If the final value previously was 1, now the final value is after modifying the final value is 6. What is the use? Response has changed completely. Right? So this is the response. See here, it is -1. The other pole is at -2. Right? And the third pole is at what location? -6. So only for the insignificant part we need to do the time constant form. Yes, Samanvay Das, only for the insignificant factors we just need to convert it into time constant form. The third is -6, right? So see here, 1, after that you have 2. The distance of 1 from the j omega axis is 1. The distance of 2 from j omega axis is 2. It is less than 5 times, right? Therefore 1 and 2 both will be dominant. 1 and 2 both will be dominant, right? So for the first pole, if the second pole falls within 5 times distance, then both will be dominant, right? So this is also dominant. So you have to consider this pole and 5 times of distance from this. 5 times of distance. See, what is its distance? Its distance is 2 units. 5 times of this distance is 10. Therefore, all the poles should be less than having a real part less than -10 in order to be insignificant. So 6 cannot be removed. 6 has to be stayed, -2 has to be stayed, and -1 has to be stayed. Right? You cannot remove 6. See, not exactly same, but similar. That is what I wanted to say. See, this is not exactly equivalent to this. This is approximately equivalent to this. So basically, systems having poles at different locations are generally overdamped systems only. So overdamped systems response will be like this. So I'm just approximating the response. I'm just approximating this overdamped response with this. Not exactly same. This red line and blue line are not exactly same. So all the poles should be having at least -30 or lesser real parts, only then they are insignificant, right? So see here, the transfer function of a plant is T of S is equal to 5 by S plus 5 into S square plus S plus 1, right? So T of S is given as 5 by S plus 5 into S square plus S plus 1. So in order to know whether this is insignificant or not, you should know what are these poles, right? So factorize this into its poles, right? So S is equal to, the poles of this are S is equal to -1 plus or minus under root 1 minus 4 by 2, right? This is minus 1 by 2 plus or minus j root 3 by 2. So the poles are minus 1 by 2 plus or minus j root 3 by 2, right? Therefore, the real parts of the poles are minus 1 by 2 plus j root 3 by 2, and the other pole is at minus 1 by 2 minus 1 by 2 minus j root 3 by 2, right? The distance of these two poles, the distance of the first two poles from the j omega axis is how much? 0.5 units, right? So 5 times of 0.5, it is minus 2.5, right? Therefore, all the poles should be to the left of this line in order to be insignificant. If there is any pole, that should be to the left of this particular line in order to be insignificant. So where is the insignificant pole located? It is located at minus 5. So you can eliminate this particular pole. You can eliminate this particular pole. Before eliminating that, you have to convert it into which form? Time constant form. Therefore, T of S is equal to 5 divided by 5 into S by 5 plus 1 multiplied by S square plus S plus 1. This 5 and 5 gets cancelled, and you can straight away eliminate this. Therefore, it will be 1 divided by S square plus S plus 1. So option D is the correct answer. So a plant has an open loop transfer function Gp of S is equal to so and so. The approximate model obtained by retaining only one of the above poles, which is closest to the frequency response of original transfer function at low frequency. So frequency response and all these terms you'll understand later. Frequency response terms and all these things you will understand later. But just use the dominant pole concept on this transfer function, that's it. So where are the poles? One pole is at minus 0.1. First pole is at minus 0.1. Second pole is at minus 2. And the third pole is at minus 100. Right? So 5 times of minus 0.1. Yes, very good. 5 times of minus 0.1 is minus 0.5. So the second pole is at least 5 times far away from this, which means this is insignificant as well as this is also insignificant. If the second pole falls under this, then you have to calculate 5 times of this distance. Only the poles lying to the 5 times of this distance will be insignificant. So the poles lying in the intermediate distance will not be insignificant. Is it clear now? Right? So you can eliminate this minus 100 and minus 2. Before eliminating them, what you should do, you just need to convert them into time constant form. Therefore, Gp of S is equal to 20 divided by S plus 0.1, S by 2 plus 1, S by 100 plus 1. So it is 200. Therefore, 0.1 divided by S plus 0.1. So this will be the correct answer for the question. Option A.